So, so I'm going to show you. Okay, well, let's go to now we're going to go with spatially progressive waves. So these are ocean waves from an example day. They're progressing towards the beach. So it's not just sigma t anymore, or 2 pi j over t over tau. But now there's a spatial element too, that it has a wave number with an x and for us to cross shore and a y component. And so this makes it into a progressive wave. And again, there's still a phase for each frequency. All right, that's progressive waves. I can group the last terms, kx times x, ky times y plus phi, into something I'm just calling theta, which is the spatial phase map. So it's got the information about the x and y variations plus this single scalar phase. And now I have a form which is going to be particularly useful if I Fourier transform in time, then look at the phases, they're going to look like this. So theta is kx, the x component of k times x, ky times y plus phi. And that has all the information on wave number that we need, particularly if you take the gradient of theta with x, so d by dx of this, the only thing you get is kx. So that's how you'd find kx if you had phases, a map of phases. If you take the gradient of theta with y, the only thing you get is ky. And so that's how you would find wave number, is looking at phase gradients in a phase map. And if you've got kx and ky, you can combine those into the magnitude of k and the wave angle, which is the arctangent of the ratio of the two. Okay? And this is the day I'm going to show you phase maps from this day. So we collected pixel time series everywhere on this thing, and according to that grid that I showed you, the little blue dots. And then you take a Fourier transform in time, and you end up with this. And I'm going to show you, oh, by the way, this calculation is all done in a routine called find k alpha phi. Are people going to be able to get this talk?
Yes.
Okay. So you can write notes, but so here it is. Here's intensity maps x, y, and t. Here's our supposition that we're doing a Fourier transform in time only. And then we've got these spatial terms which we group into theta. And these are phase maps. Here are 3 example frequencies. So when you do the Fourier transform, you get frequencies, you get 1,000 frequencies. And so there's 1,000 of these dudes. I'm just showing 3 as an example. Let's look at this little middle one. So the frequency is 0.0758. So whatever that is, 13 seconds or something. The inverse of that. So that's for that particular frequency band. It's a map. So here's X. That's the beach going offshore. Here's Y. The pier is here. And what you see, and we're plotting phase. So phase goes between minus pi and pi, the way I've got it plotted now. And you see the waves. You see the wave patterns. And it goes, let's see, it goes from blue. Well, the way this is going, it's going red into yellow, into whatever, into blue, and then it jumps from blue to red. And so it's going through a series of phase ramps, which are the pattern of the waves at that frequency. And where they jump, if you go from a jump to another jump, that's a wavelength. Or more in general, if you look at any little area here and you look at the slope, d theta, dx, that's kx. So, okay, we're going to do this a little more slowly. So, that's the concept. Let's bring this into cBathy now. cBathy does its analysis in 3 phases. The workhorse of the whole thing is phase 1, and it's finding the K alphas. So you're going to find a suite of frequencies. You had 1,000 of them. We're going to pick 4 best. And then we're going to find for each of those from the phase maps, we're going to find the wavelength, that's the length between those cycling phases, and the direction, which is you can actually see in those phase maps also. Then in phase 2 of cBathy, we're going to take a bunch of frequency wave numbers, and we're going to find a depth that best matches a whole bunch of those in a little local domain. Then phase 3, well, I should really just leave phase 3 till later. That's after you've done most of the work in order to smooth noisy results. Just showing where we're heading. Bathymetry, when we do a Bathy result, the variable has a whole bunch of information in the structure. Everything about phase 1 is kept in a substructure called F-dependent. So this is because we're saving the frequencies and the wave numbers, and we'll look at these. The second phase has a structure called F-combined. So we've combined the information from a bunch of different frequencies and made a single depth. And then running average is the Holman filtering. Okay. A little bit more on the guts of how this happens. And you don't have to remember this, there's no exam, but it's good for you to know about it at least once. So the analysis is done on a tile by tile basis. So if I want to know the depth here, so this is the red asterisk, I use phase map information from a local tile of information. And that's the green dots here. And so those are the pixels I'm going to use in analysis to get a single depth at this estimation point. And it's weighted, it's center weighted, so it's not as big a domain effectively as it looks like. So if I blow up and just look at this set of phases, and actually it's at a different position, but it doesn't matter. These are the phases within the tile. This is X, and it's just over, well, the data is over about 50 meters, and Y, the data is over probably 100 meters or so. And these are the individual phase estimates from each of the sample locations, the 5 by 10 meters that we got our data. And you can see the phase goes from dark blue sort of here through lighter blue, through yellow, red. So it's going up in phase until it goes from red precipitously back down to blue, and then it'll do another cycle. So that's basically a wavelength. These are the observed phases. And I'm going to use the assumption, and this is just for some example frequency. I'm going to do the fitting of these things to this concept, KXX, KYY plus theta. And from that, I can find magnitude K and magnitude alpha, solve for those. And I'm going to do this for different frequencies because there's different waves on any day. And then I'll save a whole bunch of these pairs for later depth estimation. Okay, so phase 1. We're just trying to get FK pairs. Yeah.
If your waves are coming in significantly off normal to the shoreline, do you need to rotate the dial to make
No, and they're always going to be coming from different directions, different wave trains. And so it finds the angle, best angle for each estimate.
It will get confused if you have a wave field where you have like crossing wave trains at the same frequency.
Is that an observation? Because I'm about to say why it shouldn't.
Okay. My experience it will.
Okay.
In the color map, you showed different troughs and peaks there. It looked like the plot was sliced. Like, I was wondering why there were like those segments. Yeah, right there. You go forward.
Yeah.
Right there.
Like the discontinuities and things like that. Yeah. So there's two things that enter. Some of them are camera seams, and there's can be slight differences. For example, if you don't have your geometry exactly right, then you would look at see a phase jump. And there's also places, some here, where if the amplitude at that frequency at that location is close to zero, then the phase is poorly resolved, poorly defined. And so there's places it just doesn't do well.
There are a couple of sharp lines. Those are
Yeah, that's a camera seam. That's just I don't know why that's there. But in the analysis that we're going to do, we're going to pay, I better just tell you, we'll pay attention to how coherent a pixel frequency is contributing, and we'll wait out some of the stuff that is looks like it's just in the noise. But let's keep going and see how that works. Okay, so when you go through the calculation, the first thing you do, and this might sound counterintuitive, you do a Fourier transform. So we said we're doing that in time. And the first thing you do is you normalize it. So you take away the magnitude. And the only thing left is phase. So these were A plus IB type things. You make them all the same magnitude and only retain the phase, the arctangent of B over A. So that there is no sense of magnitude of different Fourier contributions into the signal that's going to follow. It's only phase that we're going to care about. And that is probably pretty important for waves, because when they break, they got big signals. And some of the stuff we're going to look at is really subtle signals. And we only care about the wave phase, so we don't want to be overruled by big splotches. So we do that first. Then we calculate what's called a cross-spectral matrix, where you do a cross-spectrum of every pixel within the tile with every other pixel in the tile. And in an early version of the algorithm, that was the basic product. Oh, and that's over a bunch of frequency bands. I'm going to mention quickly, this algorithm is designed to be used every day, anywhere. And every day, the frequency bands that are contributing to the waves you're seeing vary. And so the algorithm has to allow for all the possible variations of waves, frequencies and directions that you can see. So we will choose a bunch of possible frequencies from a minimum frequency to a maximum frequency. And it will look through all of those. For each, when you find cross-spectral matrix, you can derive the total coherence between all the pixels. And you can find a sum statistic out of that entire cross-spectral matrix of the total coherence. And we are looking for the most coherent wave phase maps. And so we will take the frequencies that we choose for analysis would be the top 4 coherent maps that it sees at that pixel tile. And 4 is your choice. But so we'll show you that more by example. The next step, which is something that is meant to address what Kate was talking about, is you've got a cross-spectral matrix, and we do a complex EOF of it. So the idea is that within a frequency band, you might have waves. Normally, different wave trains come at different frequencies and different directions. And so they'd be sorted out by frequencies. But it's possible you can get, in the same frequency band, waves coming from different directions. If you do a complex EOF, it sorts those into coherent modes. And so the idea is it should sort out the waves that look like they're coming from here, away from the waves that are coming from there. It may be if it's a reflected thing, that each of those is still coherent. That may be confusing. But if on an open beach where it's just input waves, you do an EOF. That also has an advantage. It comes up, it produces a phase and amplitude map of the EOF. Yep. And I'm not going to go into details of what an EOF.
In that case, does it tell you what percentage of the waves are coming from that direction as well?
It tells you what fraction of the cross-spectral maze variance is explained by that mode.
Okay.
Yeah, that's wave number, or lambda. With eigenvalue. Yeah.
So the cross spectrum computed for the phase?
It's from the phase data, XY phase, and it's cross spectrum, so that is an average statistic over a series of slices in the spectral band, a series of different frequencies. It makes a cross spectrum out of those. It'll be hopefully a little more obvious than that. So we do the EOF, and then our basic model again is that the phase maps look like the two wave number components plus a phase. And so we make a guess at what the two components of wave number are, and we produce a model prediction of what the phase map should look like. We compare it with the observed phase map. There's a weighting here, which includes a bunch of things like especially how far the pixel is from the center and a bunch of stuff that goes in it. Then you do a nonlinear least squares fit to find kx and ky, the best kx and ky. And so it's trying to match, I'm pointing to my screen, this observed phase map, and this is actually the predicted phase map. So it found a kx and ky, or a magnitude of k in a direction that gave this prediction, and this should look like that. And so when you do the nonlinear search, that's what you get. And so if that's successful, then you've got a good kx and ky or k alpha, and then you're happy. So that's phase one. And that's the heart of what it does. It produces a structure called F-dependent, so it's got all the frequency information in it. It has this structure, we'll look at this. So it's got the frequencies. I usually ask for 4 frequencies. So it'll be 4 frequencies. If it doesn't find a good solution, like if there's only one good frequency, the rest of them will be nans. And so it doesn't get, it's low stress about that. The wave numbers and the directions. And then if you've got a frequency and wave number, you could find a depth. And so this would be the depth that corresponds to those single pair with the dispersion relationship. We don't use this except for debugging. And I'll show you what happens in phase 2. These are the errors of all those estimates. Here's some diagnostic things. This is the skill of the fit. Degrees of freedom, how many independent points went into that. Relative magnitude of the first EOF. So how important was this EOF compared to noise? And then some other stuff like the number of pixels in the tile, how many times it had to iterate to find a solution, and some seeds. And if a tile crosses a camera boundary, this is only important in multi-camera stations. It can have those discontinuities. And so we tried to figure our way around that. We finally decided we will only take the tiles, the pixels from the dominant camera, the one that has the most pixels. And so it'll say which camera those came from. Okay.
Hey Rob, should we pause for questions about phase 1 before we move forward to phase 2? Or is everybody either so overwhelmed?
Well, the thing is, yeah, part of what is going to happen now, I'm going to do, phase 2 is really quick. And then we're going to do a demo, and we're going to actually pick apart an example, and you're going to look at all of these structures within the tides. You can look at phase maps. So it might, some of the stuff may just clarify naturally, but you can ask questions. Yeah.
Just a couple. How did you choose the tile size?
tile size?
Yeah, we've got a 200.
Actually, it used to be that you chose the tile size, now you don't. So we found out that you could get enough of a guess from those phase maps to guess at what the light wavelength is. And then it actually makes a tile size, which takes that guess, and it makes a tile size that's actually, I think, 1.15 times that scale. That turned out to be sort of an optimum tile size.
The last thing is,
That's for phase one. For phase two, it's smooths over more of a smoothing.
do you have to choose that light scale as well? Or?
Yeah, you do have to do something like that, but it's pretty straightforward.
And then you answer that you're not including wave current interactions, but this is also kind of assuming slowly evolving tree that the slope of the bathymetry isn't large over the change of the tree. Have you noticed that there's really significant changes?
It actually handles sandbars pretty well. We'll look more at performance on this, but I worried at first that we were trying to do mapping over a tile, assuming it's a constant depth.
Yeah.
And there should be a little correction on this end and a little correction on the other side. Turns out the first order was constant, but second order we don't. But
So related to this question is, all this is based on linear wave dispersion,
yeah,
linear dispersion, which best describes linear waves. So if you have nonlinear waves,
we still have all this one.
There are certainly errors during larger waves,
yeah, exactly.
Yeah,
But there are actually other errors that would be larger than linear dispersion errors.
So you have looked at nonlinear wave dispersion to quantify the difference between linear and nonlinear dispersion.
People have.
yeah. You would need a measured wave height in order to use the near,
so
The correction is dependent on wave height. So
which we
that's
don't
why.
have, yeah.
But you don't have, we can measure.
there are worse problems.
Yeah.
Yes, there are worse problems than that.
So this
Ends up being a little bit even
people
worse.
happy, so I'm passing it up to one. Okay. Phase two is easy compared to phase one. So the idea is, again, this is a linear dispersion relationship. We now have a bunch of FK pairs at a bunch of analysis locations. So we've gone through, and all those little red dots are nearby locations where we've done phase one. At each one, we've got 4 frequencies and wave numbers. We want to combine those into a single depth. So if we look at this point, the original point, and look at all the FKs around it, we want to combine the information from the 4 frequencies at each one, including some spatial reach out in the tile, and find a single depth that explains all of those. The reach out, the other points here are distance weighted, so guys that are farther away are less important, etc. And so then we're going to do a nonlinear search that finds a single depth that best fits all of those FK pairs. We'll save that along with its error and a thing called F bar, which is the weighted frequency. So everything we've done here is to estimate for one location what the bathymetry is. And now we do that at, I typically do like 25 meters in X spacing and 50 meters in Y or something like that. I've forgotten what it is. And then we'll do that and step around doing the entire process and then make a map of bathymetry. Before we do this, I'd love to show some of the results. You know, for all the imperfections that are in this thing, it's somewhat amazing what it does. So I'll show a series of plots very quickly. This is from 2010. These are actually phase 3 results, so these have been Holman filtered, but they're still beautiful. These are survey measurements, 500 meters in the cross shore, kilometer in the longshore. This is cBathy estimates, phase 3 Holman estimates. And there are anomalies near the pier, So I've just kind of highlighted that area. Don't be too stressed about that. In the 2010 paper, we took 16 surveys from 2 years, and we ran hands-off analysis from cBathy, phase 1, phase 2, and then again, at that time, you had to use Holman filter to get better results. We'll talk about that later. And we did a turnkey comparison with all the statistics. And I'm just going to show a bunch of these. It's all hands-off, but I'm impressed with how well it picks up even small details in bathymetry. And there's differences, but it's pretty impressive. And as we went through that data set, there was the bias over the entire data set. Hands-off, turnkey stuff was 19 centimeters, and the global RMS was 51 centimeters. So we were pretty happy with that. That's version 1. Also, I got a kick out of this one, which was the Netherlands. And there was a student, Leo Sembring, who had never tried cBathy before, and he tried it. And I thought, the Netherlands, the North Sea, has very short period waves, so I wasn't sure it was going to work at all. And he tried it. This is ground truth from a jet ski survey. This is cBathy. And these are 4 transects. Those are the transects. And he came in and he showed me this thing, and he said, "Do you think this is okay?" People would die for this. So anyway,